are seeing my slides, right?
Yeah.
Full screen?
Not yet.
Okay, now it should be fine, right?
Yeah, now they're fine.
Okay, so thank you very much for this opportunity to present this first work, basically on a human and physical human-robot interaction with aerial vehicles. And this work has been done while I was at LAS together with Dr. Rashid Alami and Bruno Siciliano from University of Naples. So as we saw during this workshop, we can already find many solutions for physical human-robot interaction, but in most of these cases, the robot is always a ground manipulator. On the other hand, currently we are seeing a great improvement of physical interaction capabilities of aerial robots. But why we cannot find solutions or works on physical human interaction with aerial vehicles? This is mainly due to the danger for the human while interacting with an aerial robot. And this is because we need to manage these complex tasks. We need to address several challenges, including the complex interaction with an uncertain dynamics that is given by the human, and of course the methods that the robot should be safe and robust with respect to uncertainties and external disturbances. So for this reason, in this work, we addressed one of the first systems in which an aerial vehicle is tightly coupled physically with a human. In particular, here we have an aerial vehicle that is tethered by a cable to the hand of a human. Here, the objective is, first of all, to design a robot that is safe for the human, having a compliant robot. And the objective of the robot is to guide the human along a desired path or toward a desired destination using only forces. This because we foresee an application, for example, involving blind people. And of course, we want to design a system for which we can ensure stability and robustness. So for the first objective, the one of having a compliant robot as done usually in the state of the art, we implemented an admittance filter on top of a position controller. And this basically allowed us to model both systems, the human and the robot, as a mass damper system connected by a spring that here models the cable. And to perform the guiding task, then we add an additional input that is the force that we want the human to feel. And looking at the similarity of the system with a flexible manipulator, we then have been inspired by this literature to then design this control input UA that is composed by two components. The first is basically an attraction force that brings the robot toward the desired configuration, while the second term is an additional force that prevents the cable to become slack. And thanks to Lyapunov theory, we managed to prove that the final desired configuration is asymptotically stable. Furthermore, we also proved that the system is passive, which guarantee high robustness with respect to uncertainties and external disturbances. And finally, to perform the path following task, we also design a maneuver regulator. Here it is the final experiment where the aerial vehicle takes off, the human starts in a safe position and can grab the handle. Once this is done, then the robot can start pulling the human along the desired trajectory. The latter is not known by the human in advance, and in this specific case, the human is not blind, but is asked not to look at the aerial vehicle in order to have a visual reference, but just to feel the force and follow those toward the final destination. When the human arrives to the final point, the aerial vehicle will be just on top of him, and so it will understand that he arrived to the destination, and so can release the handle. So thank you very much for the attention. This was a very brief presentation of this work, but I invite you to look for the details on the full manuscript available on arXiv. And of course, I remain available on the Slack channel. Thank you very much.
Thank you, Marco. Very nice work. So I would like to remark to the audience that questions are moved to our Slack channel. So to move forward, I would like to introduce our next speaker, that is Santiago Iregui. He will present generating reactive virtual fixtures, reactive guidance virtual fixture for assisted telemanipulation tasks. Actually, Santiago sent us.
Yes, I am online and ready to take all the questions from the audience through the Slack.
All right.
Thank you, Maria.
I will share your video.
Yes, thank you.
It works.
Hello, everybody. My name is Santiago Iregui. I am a PhD candidate from the University of Leuven in Belgium. And today I'm here to talk to you about our work on generating reactive virtual guidance fixtures for assisted telemanipulation tasks. This work was performed with the motivation of assisting with spinal cord injured patients with different levels of mobility during daily tasks and help them to improve their quality of lives. The assistive strategy that we are going to present was developed within the constraint-based task specification and control framework ETACEL, whose reference you will find at the end of this talk. In order to understand the properties of the reactive virtual guidance fixture, let's first start by observing its behavior in a human-in-the-loop simulation. The green sphere, which is controlled by the human operator through a 3D connection space mouse, represents the position of the end effector of a robot. You can observe that a human can drive the end effector freely inside the volume of a yellow tube-shaped virtual fixture. Outside this volume, an impedance attracts the end effector of the robot towards its interior, resulting in effective guidance of the operator towards the goal. The proposed virtual fixture reacts by adapting its shape for two different purposes: to comply to changing goals while snapping to intended targets, and also to guide the operator through a collision-free volume by avoiding dynamic obstacles. In this work, for demonstration purposes, the operator controls the target position with a joystick. The shape of the tube adapts to follow the changing target while preserving the geometric shape learned from a set of demonstrations, which are performed by kinesthetic vision. The learning algorithm is based on a probabilistic principal component analysis, and it is described in the reference below. In this example, we have three objects, which are detected by a commercial vision system when using it in a physical setup. Our assistive strategy infers the intention of the operator and attracts the endpoint of the tube towards the inferred target object. This attractive behavior is achieved by setting two conflicting sub-constraints. The first constrains the endpoint of the tube to go towards the operator's target position, specified in this case with the joystick. The second constrains the same endpoint to go towards the position of the inferred object. The weights of both conflicting constraints are modulated according to the posterior probability of wanting to grasp the predicted object given the operator's target position. This results in a shared control between the operator and the computer. The Mahalanobis coordinates are just normalized position coordinates in the plane where the objects are located. You can observe how the control regions look like as a consequence of the Bayesian intent estimation algorithm and the aforementioned modulation of the weights. The second reactive behavior has the purpose of guiding the operator through a collision-free volume. Here you can see how the shape of the tube adapts when a dynamic obstacle moves towards it. Protective spheres are placed along the tube for setting the collision avoidance constraints. The left and the right simulations are practically the same, with the difference that in the right the protective spheres are shown. The spring-like behavior obtained is similar to the one described in the elastic struts framework, which is referenced below. Here you can see how a human operator controls a 7-degree of freedom robot arm with assistance of the reactive virtual guidance fixture. The orientation of the end effector is autonomously shifted from an initial to a final orientation. This is achieved by setting the orientation as a function of a normalized path variable S, which indicates the progress of the end effector along the tube. Now, imagine that a thirsty operator wants to grab a drink from the fridge. The commercial vision system detects a beer, a juice, and a milk, and provides a tick impulse for each. Obviously, the operator decides to go for the delicious beer and indicates it by means of the human machine interface. In this case, for demonstration purposes, the joystick. Afterwards, the operator decides to grab also granadilla, a delicious fruit found in Colombia. The vision system was not able to detect it, so the tube is not able to snap to it, but still he will be able to get it with a little more effort. Here you can see how the operator is guided to the target in the presence of a dynamic obstacle. Protective spheres are also placed in the tube so that the operator is not able to move the robot out of the tube in the direction of the obstacle. In a later phase of the project, we plan to perform clinical trials in a physical setup for validation. We expect that operators with different levels of mobility are able to control the robot with a significant reduction of effort and previous training. In addition, different human-machine interfaces are being explored to be used in combination with our framework. For example, a novel visual motor brain-machine interface that is being developed by our project partners. Finally, I'd like to thank you all for listening and wish you a very nice day.
So the next, Marco, would you like to introduce the next?
Yeah, so thank you, Santiago, for the nice talk. So the next speaker is from University of Leeds, and it should be Rafael Papallas. And this work is about optimization-based motion planning with the human in the loop for non-prehensive manipulation. So thank you.
Yeah. So let me share my screen. Okay, great. Can you see my screen?
Yeah.
Yes.
Okay, good. In fact, sorry, just give me a second. Hello, everyone. My name is Rafael. I'm from the University of Leeds, working with Dr. Dogar and Professor Kohn. Our work is on optimization-based motion planning with human in the loop for non-prehensile manipulation. We're interested in tasks where the robot needs to reach for an object from the back of a cluttered fridge or from the back of a cluttered shelf, and the robot needs to consider ways to work in these clutter environments. So you can think of a robot trying to reach for an object from the back of a fridge or from the back of a shelf. So for people who are not very familiar with manipulation, non-prehensile manipulation is manipulation without grasping an object, which could be that the robot considers actions like pushing or pulling to manipulate the environments. And the motivation of such skill set is that sometimes some objects are ungraspable or heavy, or it could be inefficient to pick and place every blocking obstacle just to reach for the goal object. So you can see the robot there is trying to reach for the green object, but before doing that, he is working in the clutter, pushing objects just to make space to reach for that object. There are four main problems that we need to consider in this problem. First is a high dimensional space, meaning that the robot needs to consider multiple objects and the state of these objects. But more importantly, the robot needs to consider which objects are important for a given problem and how to work with those objects. Second is an under-actuated system, meaning that the robot needs to generate the right motion to indirectly manipulate those objects, because obviously the robot cannot control the objects directly. Third, to do this and to predict the future state of the robot action, we need the use of a physics simulator to predict the future state, but these physics simulators usually are very computationally expensive. And finally, as Khatib mentioned earlier in morning, the presence of uncertainty in unstructured environments could be problematic, and we have to consider physics uncertainty because the simulator will never be an accurate representation of the real world. So we propose an online replanning framework with human in the loop to tackle these problems. So we have a real world environment, and we perceive this real world environment in simulation. Then we employ stochastic optimization to solve the problem. By the end of the optimization, it could either be that we solve the problem successfully, so the robot successfully autonomously solve the problem, or the robot realizes that needs help. Let's say that initially the robot finds autonomously a solution, so then we extract the first action of the trajectory and we execute it in the real world. So we just execute the first action, then we perceive the real world state again, and then we optimize with the trajectory of the previous iteration. So we warm start the optimization. And then let's say at this point that the action of the robot in the real world resulted in a state different than the one predicted by the simulator, so physics uncertainty. So the robot now failed to optimize the trajectory. So it realizes that it needs help. So we have a remote human operator sitting somewhere. and the robot asks for help, we have an interface that allows the human operator to provide a high-level input. And then we take this high-level input and we create an initial trajectory integrating this high-level input. And we also inject the high-level input into the cost function of the optimization. Then we re-optimize using this high-level input provided by the user. Let's say now the robot was able to solve the problem. We execute the first action of the trajectory in the real world. We perceive the real world. We re-optimize by warm starting. This time, let's say that the uncertainty was not a problem, so the robot continues executing autonomously the trajectory, and so on. So the important thing that we need to focus now is how do we realize whether we need human help? So we implemented two ways to realize this. First, an obvious one, which is a fixed time out. Basically, the robot will optimize for X seconds until unsuccessful and then ask for human help. It's an easy and straightforward approach. However, it's hard to choose a good value that suits all the problems and could be problematic when we have easy or hard problems with long or short timeouts. And the other one we implemented is an adaptive approach where we ask for human help when we stack in a local minimum in the optimization. And the advantages of such approach is that we don't need any more a fixed value. We leverage the cost value between iterations to decide if human help is required. And for trivial problems, the robot can solve them fully autonomously. We run a number of experiments in simulation and real world, and we observe that our approach yields to more successes in execution in the real world and in simulation, and reduce the planning times considerably, and that with a low human engagement time of 2.5 seconds on average. So I'd like to thank you for your time.
Thank you, Raphael. Very nice and interesting talk. I would like to move to the next speaker, that is Oliver Rosler. He will present an abstract titled Enhancing Unsupervised Language Grounding Through Online Learning. Oliver, are you there?
Yeah.
All right. So Oliver has some issues accessing to the Slack channel, so I would recommend directly asking questions to him by contacting by email, maybe.
Can you see my screen?
Yeah. Yes. Right.
Okay, so I would like to present work on enhancing unsupervised language grounding through online learning. Let's start first with some motivation. So natural human collaboration requires robots to understand natural language. And to understand natural language, they basically need to be able to create mappings from words to percepts. So to basically ground words through percepts. And in this study, I will present an unsupervised online grounding framework for grounding of synonymous words, and an evaluation through an HRI experiment of the framework and a comparison to a Bayesian offline grounding framework. So let's start with the description of the experimental setup. So basically, we have an HRI scenario where a tutor and a robot are interacting in front of a table, as illustrated on the right. And it has a three-step procedure. First, the tutor places an object on the table, and the robot obtains its shape and color percepts. Then the tutor provides an instruction, for example, raise the brown Coke. And finally, the robot executes the requested action and records the corresponding percept. Overall, 125 interactions are performed for all combinations of the employed 5 actions, 5 colors, and 5 shapes. The sentence structure is always the same. So we have one optional auxiliary word, please. Then we have an action word followed by the article the, a color word, and a shape word. And the word please basically occurs about 50% of times and 50% of the sentences. We have 2 synonyms for actions and colors and 5 synonyms for shapes. And they are not true synonyms, but basically synonyms which are only synonyms in a specific context. For example, if we have a bottle, then we refer to it by Coca-Cola, soda, Pepsi, words which basically refer to the content of the bottle and not the bottle itself. Then the proposed framework is structured as follows. So we basically obtain visual information using a stereo camera, and then 3D segmentation is used to extract point cloud data for each of the objects. And then viewpoint feature histogram descriptors are extracted from the point cloud data to represent the geometric characteristics of the object. Additionally, from the point cloud data, a color histogram is created, which represents the color of the object. Then we have an instruction, please raise the brown book. And cross-situational learning is used for auxiliary word detection, so to remove the auxiliary words so that we just have the non-auxiliary words, which need to be grounded through corresponding precepts. And then finally, we have an action feature vector, which is a 30-dimensional vector obtained by recording 6 different joints and how they change during action execution. Then normally we want to give the precepts and the instruction to the grounding algorithm. However, the proposed grounding algorithm requires the precepts to be represented through an abstract representation. And this is obtained through clustering, in particular through dbScan, because dbScan doesn't require to specify how many clusters we have in advance. For the baseline model, it's a little bit different here. So we don't require clustering. We don't require before the grounding auxiliary word detection, but it directly gets the raw percepts and raw instruction because it basically has integrated clustering. And then 10 different sequences of situations are created to ensure that the order of the situations doesn't influence the grounding performance. And then only 60% of the situations are given for training and 40% for testing, because the baseline model requires a training and test set, while the proposed model does not require this. So it can basically normally continuously learn, but to ensure a fair comparison, it also only gets 60% for training. And these are the obtained results. So as we can see, the proposed model outperforms for all modalities the baseline model. Biggest difference is seen for shapes, and this seems to be because for shapes, there were 5 different synonyms, and the baseline model requires more situations than the 60%, so which are basically 75 situations which were used for training. And again, the proposed model normally can continuously learn, so it was basically artificially limited to 60%. So to conclude, the presented online grounding framework outperforms the Bayesian baseline framework. And in future work, I will evaluate it for more complex sentences because the used ones were quite simple from the structure. And I also will extend it to learn from human feedback. So to add, if we have human feedback, that it can also enhance the sample efficiency as well as the grounding accuracy. Thank you very much for your attention. And yes, if you have any questions, unfortunately, I don't have access to Slack, so please send me an email. Yeah, thank you for your attention.
Thank you, Oliver, for the nice presentation. We move to the next speaker. Last but not least, there is a work from Dipartimento di Ingegneria Informatica, Automatica e Gestionale from Sapienza University of Rome. And there should be Marco Ferro presenting this work about a framework for sensorless identification of lineal tissue interaction forces in robot-assisted biopsies. So Marco.
Yes.
Please go ahead.
So I'll share the screen. Please confirm me that you can see correctly the...
Yeah, I see the screen.
Okay. So thank you, Marco, for the introduction, and good afternoon, everyone. So in this short talk, I will present a framework for sensorless identification on linear tissue interaction forces for robot-assisted biopsies. The introductory consideration is that for many robot-assisted surgical tasks, shared autonomy is a very desirable behavior, since we aim at combining the intentions and the experience of the user with the advancing the capabilities and autonomy of the robot to improve quality and safety of the procedure. This is true for teleoperated needle insertion procedures, despite we may encounter some limitations from the perception point of view. For example, we may not be allowed to measure directly forces with dedicated sensors on the remote environments due to safety constraints, or the user may have partial or limited and not in real time visualization of the virtual environments with the medical imaging systems. So we aim at coping with these limitations by enhancing the perception of both sides. And so on one side, we enhance robot perception with a sensorless identification method for the needle tissue interaction model to detect the tissue transitions along the insertion. And on the other hand, we aim to enhance the awareness of the user with a modular digital twin framework, including a real-time 3D view of the remote site inside a virtual environment, along with a 3D model of the anatomical target reconstructed from preoperative diagnostic imaging acquired. For what concerns the robot side, the identification of the interaction forces is based on a viscoelastic model and accomplished with a least square approach that minimizes the error between measured forces and predicted forces. To avoid the use of dedicated sensors in the setup, we reconstruct measured forces through the well-known computation of the residual vector that is based on the knowledge of the robot dynamic model with estimated parameters. Then we detect automatically the transitions of tissues by evaluating statistically the abrupt changes in the profile of the force signals. And here you can see here in the slides the results from both the reconstruction, the sensorless reconstruction of the force shown in orange and compared to the ground truth measurements of the sensor in blue, and also the tissue transition detection corresponding to the puncturing events accomplished on a simple isinglass gel phantom, both for automatic and teleoperated insertions. For what concerns the user part, instead, the framework is interfaced with the Coppelia Sim simulator to recreate a faithful and virtual replica of the surgical environments. The framework is inspired, the architecture of the framework is inspired to a boundary control entity software engineering pattern in order to distinguish and separate the different responsibilities within the framework itself. And so we have the communication with the external devices, the implementation and management of high-level functionalities such as cognitive or control tasks, and the local data storage and processing for each single component of the overall system. In particular, to enhance the possibility to accomplish shared autonomy behaviors, we consider the possibility to define multiple control modalities and kinematic constraints that should be accomplished simultaneously. And finally, as a last remark for this framework, the modularity property of the framework allows to generalize in an easy way the structure for any arbitrary surgical tasks. So here we show some results, some employments of this framework for a needle insertion procedure. In particular, here we considered as a more realistic target the phantom of a human abdomen on which we perform the insertion. The phantom has been, the model of the phantom has been reconstructed from preoperative images acquired from CT scans and registered inside the virtual environment with respect to the robot with a set of landmarks. In the video here, we see the different control modalities and constraints adopted for the accomplishment of the task. And our next objectives will be to validate and evaluate the sensorless identification methods presented also in this more robust scenario, more realistic scenario, and also to exploit the modularity of the framework in order to implement additional functionalities that may be of interest for a specific surgical task. I'm done, so thank you for your attention.
So Marco, thank you for your nice presentation.